and I'll let you know where things are. With the current model, there's still a bit of work to be done on getting the performance where we'd like it. So I'll talk to you about that, but I wanted to go into the process, so you're aware of how it works and a bit of the theory of it. And then also I'll show you the coding, some of the coding to look at the model outputs, and we can talk a bit about what kinds of targets you would have for the model performance, and yeah, how it looked in the previous rounds. Yeah, so I'll go into some of the issues there, but first of all, I wanted to check in. Last time we talked about inputs in terms of land cover and some of the management of the land cover and what's there in the model, the soils, aquifers, dams, and point sources. Did anybody have any lingering questions from that you wanted to pose now before we go into the calibration part? No? All right. Um, I have been working towards altering the land cover for the crops, as we mentioned, to incorporate wheat as a winter crop, using some of the default parameters and then looking up information from Department of Agriculture on that it hasn't made a big difference to do that so far, but I haven't looked as in depth on the water quality impact it might have, but I think it's worthwhile trying to incorporate what we know in as much as possible. So yeah, I'm going to talk today about some of the output data processing setup and a bit about calibration. Starting with some background, because I realize I presented on calibration a bit in theory quite a long time ago, and so it might help to recap a bit of that. Yeah, so that's what I was talking about there. Um, so. So I've got quite a lot of slides here. I'll go through them fairly quickly, but you'll have them as a copy in case it's something you ever need to look back at. I think it's helpful if you're going to be working with models in general, either doing modeling yourself or thinking about other model outputs, it's quite helpful to think through this critically as well in terms of what are our goals with the models, what can we use them for, and what shouldn't we use them for. In terms of their performance and yeah, how to use them based on that as well. So when I say model performance, what I'm talking about is how well does the model recreate observations? Usually stream flow, but if we have observation, water quality, but if we have observations of soil moisture or groundwater levels, the more the better, really. And then using various statistics, which are measures of error. So when I say performance, it's kind of the inverse of error. If the error is low against the observed, then we say it has higher performance. And we evaluate that with various statistics. And then process of calibration is adjusting parameter values to improve the model's performance. We can also do other structural, if like I run the model and it's very, very off in certain ways, then before I start adjusting parameters, one can look at, is there something very wrong with the input data, especially the climate, and is there something that can be changed there? And is there something off with the structure of the model, like there's some interbasin transfer or something like that's a big impact that's missing or didn't work somehow. So we do these sort of sense checks first, and then if it's looking like it's responding fairly well, but it's a bit off, then you start adjusting parameters in a calibration process. And then validation, You might have heard it, depending on how much sort of academic literature you've looked at or published studies you've looked at, and you might see calibration and validation used a little bit differently. So validation can mean checking model performance versus one's goals or the thresholds of acceptability for using the model for whatever purpose you want to use it for. Is it adequate? Another way that validation sometimes gets used is you have a calibration period and a validation period. So you look at the model's calibration, how well it recreates the performance in some period like let's say 1990 to 2000, and then for 2000 to 20, you do a calibration process to try and get performance adequate for that period of time. And then you do a validation period, which is like an independent check on the model's performance for a different time period than you were doing your calibration process. And the reason for doing that is to try and see if your model, your calibration process was sort of biased towards the time period you were looking at. But in more common, like outside of sort of modeling literature, you can also look at validation being checking the model against the goals or the thresholds of acceptability. And when you have shorter, there's a whole branch of literature that actually suggests trying to calibrate against the full time period you have, just because, especially in areas with highly variable climates. So that's the way I've been doing it, and I'm considering validation. Just is the model now good enough to use it for what we want to use it for? So I'll want to circle. I'm going to talk more about calibration and like perform different statistics and stuff. But I do want to, I will circle back during this session with you to think about what kind of checks do we want to have and goals for this modeling in particular, to know when is it good enough to use for what applications, and how you want to see the results there. So we'll circle back to that after I go through some details. But please, like, I want this to be also a discussion. So if you have questions, just unmute and go ahead and ask, because I can't always see things in the chat while I'm presenting and stuff. So do feel free to jump in and ask questions. So as I mentioned, validation is the way that one way of using it, and the way that I use it, is how good is the model? Is it fit for purpose? And depends what the model outputs are going to be used for and how much error or uncertainty is acceptable in that context. Sometimes we just have to change how we use it given what the model is able to achieve in the time that we have. But obviously, infrastructure where there's a lot of safety regulations, you want higher certainty, or you have a big buffer against the uncertainty, of more conservative, given the range of outputs the model gives you. Flood lines, land cover management, we can be somewhat more relaxed about it, in that it's not going to, the safety aspects aren't as severe, and we want to get it roughly right, but we're not going to cause major harm necessarily to make some decisions with a bit more of an uncertainty range with land cover management questions. Oops, sorry, typed that the wrong way. And then, at national scale of prioritization, or like regional scales of prioritization, focus on this area versus this area. Again, it can be a bit more uncertainty, as long as the ranking of things across one another remains the same despite any uncertainties in the model. And then research purposes as well. Just some examples. There's a lot of ways that error and uncertainty come into the modeling, and then we try and use calibration to overcome some of that. So it can come in the data, it can come from the model, it can come from the way we classify land cover. So excuse me. Measurement. So one that we often don't think about as much is that there is error in measured values. Um, and we can have an idea of how much error there might be in measured value. So that's the measured value is deviating from the real value, but how do we know what the real value would be versus the measurement? So taking multiple readings or using multiple methods to check the equipment. Often measuring equipment comes with an estimate of error ranges. There can be known shortcomings in the way that we measure things, like some stream flow weirs have a flow above which they stop capturing flood peaks well, or low flows. They also have a flow below which, they stop capturing that well just because of the way the structure is, and we may know that in advance or see it in the data. And then model error is error in the model's output predictions compared to ideally the real value, but it's often compared to the observed data. And either we assume the observation, usually when we calculate our statistics, we're assuming that the observation data set is accurate, but we account for measurement error in some way by being a bit relaxed in how tightly we try and get our model to fit our observations, because we actually know that our observations have some error in and of themselves. So if we try and make our models fit our observation data set too tightly, we might actually be not representing reality because there's error in the observations. Excuse me, I'm a bit sick this week, so my voice, we rescheduled it so many times, so I thought, let me go ahead. Excuse me. So hopefully that makes sense to everyone. Somebody have a question? I see an unmuted. No? Okay. Oh, excuse me. When there is no observed data, then we start to talk about uncertainty rather than error. But we use error so we have no observed data when we're doing land cover scenarios, climate scenarios, etc., or you're modeling an ungauged catchment. So then we use error to say something about uncertainty. We use error for a period where you do have data to say something about uncertainty. So uncertainty is a little bit different than error, because uncertainty is the range where we think the real value is going to fall, but we don't actually know what the real value would be, for a modeling scenario or a climate change scenario. Excuse me, I just need to cough.
So, Julia, maybe we
Sorry
can
about
maybe
that.
take a 10 minutes break if you're not
I'm back.
comfortable
Sorry about
then.
that. One of those ones that gets stuck in your throat. Sorry, Nsanda, were you asking something?
No, I was suggesting that we can take maybe a 10-minute break. If you're not comfortable, then we can come back.
Thanks. I think I'm okay now. I just did a good cough. But I will
Okay,
take a break.
okay,
I'll get through a section and then I'll take a break and drink some more water. And I've got some water here and stuff.
okay.
Sorry. I thought that I should carry on given everybody scheduled the time. Um, but I'm doing all right. But thank you for that. Um, so with uncertainty, and I'm sure you've dealt with this in various aspects of your work. I just wanted to bring it in context of what we're looking at with the model outputs here. It's a range where we think the real value is going to fall. and we look at it. So like in this figure, for example, there is observed data in this figure that illustrates it fairly well. Like the red line in this figure is the observed data. This is from a paper, not from our particular model, and there's months on the bottom. And the red line is the observed stream flow, and the black line is a modeled output for like one set of parameter values, for example. And then the gray band represents the full, represents an uncertainty bound that captures the observed data, in this case, about 80% of the time. And so they looked at what ranges of parameter values could they input that would create this uncertainty range where the observed, that red line, is within that band 80% of the time, because the model is an imperfect representation of reality. You're never going to get those two lines to fit exactly, unfortunately, because of errors in the input data, errors in the way the model calculates things. So you can get the sort of best fit model, which would be the black line. And you can also get a range of options of parameter values that create that gray band that capture things. Some of them capture the high flows better, some of them capture the low flows better in that gray band. And so that would be generating a confidence interval. And then the way you would use that, if you wanted, is to use those bands of parameter values when you go forward and do a scenario, and assume that it will capture the real value 80% of the time in either the climate change scenario or the land cover change scenario in a band of scenario outputs. And so, and please stop me if you have any questions about that. I hope that makes sense to people. These graphs along the bottom show the different plotting modeled versus observed data on a scatter plot, and just showing how, calibration will improve the fit, but it's still not going to be perfect, and you have this range of error between the observed and the modeled that can also be used, can be used to describe your uncertainty in the modeled output. So the less we know about a process, the wider our uncertainty bounds are going to be. And you can define a confidence interval if you have some observed data to do it with, like they've done in this figure here. So our uncertainty in our modeling comes from uncertainty the input data, which is always there. Uncertainty in our model structure, it's a simplified representation of reality. We try and get it as good as we can, but it's never going to be perfect. And then uncertainty in our model parameters, like properties of the vegetation and the soils. And some more conceptual parameters, which are things that describe like forms of equations. So when I say a conceptual parameter, I mean like a parameter that controls how quickly groundwater flows or soil flows, water flows through soils, but it's not linked to a specific, it's not directly linked to a specific property you can measure in the field. So they tend to be like rate constants and things like that. They are somewhat linked to the properties in the field, but not directly. So they come a bit from runoff coefficients and things like that. You link them to properties, but it's not, you often get values from tables of ranges of things, and then you adjust through calibration to get the values that are most appropriate. And then there's also uncertainty in the calibration data, which is different to the input data. So the input data would be like rainfall and evaporative demand. And the calibration data would be the stream flow data you're trying to fit your model to. Also, any groundwater levels, soil moisture, those things that you're trying to fit your model to, that data also has uncertainty in it. So as I said, we often don't want it to try and fit perfectly to imperfect calibration data. All of that leads to uncertainty in the model outputs. And we often don't have an exact measure of what that is, unfortunately, but we can make these confidence intervals potentially, or we use the error between the model and the observed to estimate some uncertainty bounds when we do scenario modeling. So some of the ways to put numbers on the error or the goodness of fit are these goodness of fit statistics or performance statistics. And different statistics give information on different aspects of model prediction and different types of model error. So some models will do well on the long-term mean but they might not do that well at a daily time step. They might capture the temporal pattern of highs and lows, but don't capture like their offset in terms of the value, the absolute values, but the ups and downs are proportionally right. Sometimes they get the high flows really well, but they don't get the low flows well, or they get the low flows well and not the high flows well, for a variety of reasons. So there's different statistics that capture those, and you want to look at a suite of them. Because no single statistic can easily give you all the information you would want. So we do need to look at graphs and use multiple statistics. And the model, as I mentioned, you can do well in some aspects and poorly in others. So we have to think about what's the most important for the application. And if we will try, and if we don't get the model performing as well as we'd like in some of the other aspects, then we have to decide, okay, we use this primarily to look at flood flows, and we use this primarily to look at base flows, and we use the other flows with more caution. So some statistics, you've probably seen a lot of these before, some of them maybe not. A more common one these days is the Kling-Gupta efficiency value, which is a combined statistic that actually combines in practice it combines the coefficient of determination, the NSE and a p-bias into one index, which is nice in some ways, but it can be a bit more confusing to interpret because it's combined. You don't know which one of those three aspects of the fit is causing it to be high or low. But it gets used for when you're optimizing things. Coefficient of determination, R squared, is looking at regression of a scatter plot of observed versus modeled, and that one gives you the temporal pattern. Is the model predicting high when the observed is high? Is the model predicting low when the observed is low? There can be an offset in magnitude, but the temporal pattern is being captured. The Nash-Sutcliffe efficiency, NSE, this one looks at variance as well as magnitude to some degree, and it looks at how variable is the model output compared to how variable the observed data is, and do the size, the absolute value of the variation match each other well. So it's looking at the model error, but the model error in the context of how variable the observed data is, how high is the high versus how low is the low. And that's a very common one to use because it kind of captures both the magnitude and the variability. And then root mean square error is a one that looks at error like the average error in each observation, I mean, in each modeled output versus each observation, what would the average of that be? And p-bias is the same, looking at it in percent. So it's looking at error in the magnitudes of the values, and it's averaging it. So if you have some values that are too high and some values that are too low, in terms of okay, so what with p-bias, if you have some values that are too high and some values are too low, those can kind of cancel each other out, and the overall percent bias for the whole time series will be lower. Whereas root mean square error, because each error is squared, and then you sum them, and then you take the square root again, the highs and the lows don't cancel each other out. So both root mean square error and p-bias give you estimates of the average amount of error in any given modeled output. So when I say any given modeled output, I mean like the daily stream flow value for a particular day or a monthly stream flow value for a particular month. What's the average difference between the modeled and the observed? And the same with, and then the p-bias is what's the percent difference between the model and the observed on average for any given day. Volumetric efficiency is a bit similar. It's like they'd use the absolute value of the error, and again rescaled. So I've been calculating all of these statistics. Well, I haven't been calculating KGE, but I can calculate and present it if that's one that you like to use or see. This slide summarizes what I just said as well. So there's different kinds of stats. So there's just straight up mean error, which wasn't in the previous slide, but that's just on average over the whole time period that we've modeled, is the model under or over predicting the average? Percent bias and root mean square error go a bit beyond that, and they say what's the tendency to under or over predict? They're stricter than the mean error for in a way, because they look at each individual error of each observation and either and then normalize it. Sorry, I'm not explaining that very well, but p-bias and root mean square error are stricter than just mean error because they don't let so much compensation happen between over and under predicting across the time series. And then the R squared is a linear regression fit, and it looks at patterns of highs and lows. Nash-Sutcliffe efficiency is its degree of error compared to the variability of the observed data. Now, to note, some of these statistics can be really put off by individual really high flow events that the model misses. So sometimes one big flow event that's missed, and it's like the dominant flow event in the time period that you've modeled, and for some reason the rainfall input doesn't capture it or something like that. That will put these statistics completely out, even if the rest of the time series looks okay. So they really weight high flow. Some of them really weight high flows. So R squared is less sensitive to that, but Nash-Sutcliffe and RMSE can be very sensitive to, and p-bias actually can be quite sensitive to individual outlier events. So it's important to graph the data and have a look and see if that's why the statistics are poor, and then see what can be done about that. Maybe recalculate excluding that one particular value if everything else is actually looking really good. Or see, is the rainfall data missing that event, etc. So there is some guidance in the literature about what values are considered good for these statistics in different cases. So like this paper was looking at SWAT performance under rainfall data scarcity, for example, and then there's others that have suggested other values. But so I've been trying to use some targets like these from literature, but they are a little bit abstract in that they're suggested what you consider satisfactory. But in terms of a meaning on the ground, one would also have to say, like, do I want a different value, or what does it mean to have a p-bias of plus 10? So that's a percent bias of 10 plus or minus 10%. So any individual value that the model spits out on average could be plus or minus 10% of what the real value is. That's what p-bias would mean. R squared is how well is there a linear fit? So to say what that means on the ground for an individual value is a bit trickier to interpret, but generally you want to have, it's more close to a tight fit, and the same with Nash-Sutcliffe efficiency. So I've been using standards based on literature, but we can talk about if there are certain indicators that are more particularly meaningful for your work that you would like to see calculated, and we can see what they're looking like. So as I mentioned, there are many statistics that are heavily influenced by the highest flows and less influenced by the low flows. And a way to deal with this is to apply a logarithmic transformation to the data and recalculate the statistics. And that gives a higher weight to the low flow. To see that graphically, this just demonstrates this graphically, for example. So the top graph shows different versions of a model, and the observed is in black, and this is normal runoff or stream flow, but plotted as millimeters. And you can see the fit looks pretty good, but then when you take a log of the stream flow, now it condenses. The log is like looking at exponential power, and it spreads out the low flows. So now you can see more clearly that like the blue model, for example, is way under predicting the low flows, like on a percentage basis. So that it's not so off on a millimeters basis, but as a percent of the low, you could think of it as a percent in a way. As a percent of the low flow, it's going to be off by a higher percent. So if you care about the low flows quite a lot, because of habitats for fish and things like that, or the high flows are going to make up a lot of the inflow to the reservoirs, but the low flows would be important for habitats or anybody drawing water directly from the river, etc. Those low flows would be more important to look at for those reasons. And then you can also plot the distribution of flows across a distribution curve. So how often is that flow exceeded, that level of flow? So that also helps you look at how the model is capturing across the high to low flows. So there's another example of that. So the blue line is the observed in this case, and the dotted line is the modeled. And you can see it does pretty well in the middle, but it's underestimating low flows and overestimating the high flows. And plotting it like that is just a good way of seeing that in the summary that might be hard to see in the time series graph. So I'll show you some of those for our models, but just to say what all these plots mean and why I've been making them. So like a note of caution also is that a model can give you acceptable performance, but it might not be realistic internally. Like you're trading off some aspect of the model. You're predicting, for example, like you're predicting too much flow out of a forestry area and too little flow out of an irrigation area. or an agricultural area, and then the total ends up being okay. And if we're only evaluating it by looking at stream flow, you won't know that you've done that necessarily. So we do want to do a little bit of reality checking on some of the internal outputs of the model. But it is a bit tricky and time consuming to do that fully. But this is like a problem that people write about in modeling a lot. And they say like you can get to the right output for the wrong reasons, and then when you try and use your model for a scenario, like changing the land cover, changing the climate, your level of accuracy will be quite different to your baseline model, and you won't actually know it. So you have to be quite cautious. The longer of an observed time series you have to compare to, or if you try and really look at high and low flows in your hydrograph, even if you're not so concerned about the lowest low flows for your management applications necessarily, trying to get a variety of statistics to perform well helps guard against this issue, because if you can perform well across the whole hydrograph, it's more likely that you're getting the internal processes of the catchment more correctly. So it is good even if to try and keep some of the other statistics that you might not care about as much, if possible, to get those to perform well as well. So to do all of this, to improve the model's performance through calibration, is just adjusting parameter values and trying to see if your performance statistics improve, and that would also reduce your uncertainty when you then apply the model to to scenarios going forward. So there's a lot of decisions that happen in that process. The modeler has to decide which of the parameters to adjust and what are the ranges of values to consider for each parameter that one is adjusting. Like what range of values is realistic for, the leaf area index of a vegetation, or the root depth of a vegetation, or various parameters about the aquifers, etc. And then we have to decide what performance statistics are we calculating, and when the calibration effort can stop. Have we reached our validation, like the level of validation we are looking for? There are automated ways of looking for an optimum solution, but those work well for simple models. They're quite difficult to set up for a big, complicated model like the one we're using. And when your input data is uncertain, it's not always a good idea to try and optimize against uncertain observations. Often we're just limited by the amount of effort and time we're able to give to the task. And one can decide between using a manual process where you think a lot about what kind of adjustments are going to help given the way that the model is not performing. And then you can also take an automated approach where it just tries all sorts of combinations, which is very helpful and more standardized, but it also takes, when you have a model that takes a long time to run, it's gonna test all sorts of options that maybe you can already see aren't going to work. So if you set it up in a certain way, you can reduce the time. You do some sort of combination of automated and manual in terms of how you manipulate the input parameters to the model. Yeah, so this is just what I mentioned with manual. The modeler adjusts parameter values, runs, evaluates the model, repeats. And then in an automated case, one can give some values of ranges for the parameters and the way you want it to check performance. And the software will run a whole batch of different input parameter values and evaluate the statistics. You might have an optimization routine. So in SWAT, there are ways to set up some batches of parameter sets and run them all. That come in some external software packages, and some of them used to be free, and now they're no longer free, unfortunately. But there's some coded ones that I've been trying to work out, but I've been using a mixture of manual and automated calibration. With an optimization routine, an automated optimization routine, that can take a really long time to run, and when your observed data has some uncertainties, and we have a variability across a large, complex catchment, I wouldn't suggest that in this case. So to determine a range of values for each parameter, I have to look at what values are realistic and guidance from other studies that have been using the same model in similar conditions, field data, and how some parameters relate to others so that you remain realistic to the vegetation type or the soil type. And that one vegetation type and one soil type, the relationship between them, like forest versus grass, the difference between them remains the way that we think it should be. And then in the case of having more reliable information or data, we would try and hold some of those parameters more constant and focus on the ones we're most uncertain about. Oh, sorry. This slide has a recording on it. Apologies. But that was talking about parameter sensitivity analysis. So we have talked about this a little bit. There are different ways of looking at parameter sensitivity, and that's how much the model output changes when you change the model input. And let me not dwell on this one. Sorry, this is a very texty slide, but it is with a large complex model like the one we're setting up here. It's quite tricky to do a full sensitivity analysis because you have to change one parameter at a time and do lots of runs. And there are different approaches, like do you change it by one unit of measure or to the min and the max of the likely value? And there are a lot of parameters here. So a common approach in this setting would be to look at literature values using the same software tool to get an idea of which parameters the model is most likely sensitive to. So I've done that for SWAT and pulled those out in a table that I'll show you. Then there's also setting a goal for your calibration in terms of validation. So sometimes it's just how many the number of trials you have time for, or you work until you reach a threshold of acceptability, or you do a kind of optimization run with a certain number of runs. Again, that's like a time effort constraint as well. For SWAT Plus, there are some inbuilt tools that help you change the parameters, and I'll flip over to SWAT just now and show you where some of these sit. And they are new compared to what the old SWAT model has. There are a few hitches in them to get them running nicely that I'm working out. But one helpful things that they have are you can set up runs that will change certain parameters by a certain amount. So like your root depths across different vegetation types, you can say, I want to increase all the root depths of all the vegetation types by 5%, or decrease them all by some absolute value, by 3 millimeters or 30 millimeters, etc. So you can change all the values of a certain type by a certain amount, which is really nice because it lets you keep the relationships between the vegetation types and the soil types and the aquifer types the way you think. Whereas if you adjusted each one independently, you can lose the relationships between them across different soil types and vegetation types. As I mentioned, there are some optimization tools, but they're now proprietary and you have to pay for them. And they're quite challenging to set up with a complex structured model the way this one is. We've got interbasin transfers and reservoirs and lots of other things going on, point sources that are playing a large role. So yeah, here's my table of parameters that have high sensitivity rankings in the literature for using SWAT for flow. And then for water quality, it often really depends on the inputs of the point sources and then the processing rates in the stream. And then also the inputs on the land cover, which are, rather than parameters, those are input data. So I wanted to come back. I'll come back to the slide again. I think what I'll do is I'll show you some of the calibration outputs so far that I produced in the previous round of the modeling and where we are with the new one, and then come back to this slide. But I'd like us to chat a little bit about what kind of error statistics or uncertainty statistics and goals we would have for this model. So I can be sure that I'm also calculating those and presenting them and writing code for you to get those out in the future. I do want to pause if there are any questions at this point, and then maybe we take a little break. I'll present some of the output stats. So far, I'm trying to get the new model to perform at least as well, if not better than the previous one, but there are a few hitches that I'll talk about, but we're getting there. And then we can come back and talk about what are the kinds of performance stats and the kinds of goals for the modeling in terms of where we should aim and what to present. But are there any questions up to this point? I'm not seeing anything. Can we break until 10:15? Think?
All right.
Is there any? All right. Let's break until 10:15. I'm just gonna pause the recording and I'll see you guys shortly. If you think of any questions in the meantime, I'll take those when we come back. All right, or you can post them in the chat as well. Hi, everyone. Hope people are back, and just give me a thumbs up if you are back in the room. You guys are back in the room. All right. I'll keep going. I've restarted the recording, and yeah, I left off with. Yeah, sort of given our thoughts on what the model is going to be used for, and then understanding the limitations of the modeling and the data, we want to just think about what we're aiming for here. I'm going to present a little bit about the output processing that goes into checking how well the model is doing, and then I'll show you some of the results of where things got to with the previous model, and we can talk and where things are now, and then we can talk about any inputs you have in terms of what you'd like to see presented more specifically going forward, because I'll show you a bit about the coding now, and we can code up various things, and then where we might be able to get to with calibration to finalize, and then work on. I believe the idea is that it's something that we'll get to where we can get to for this round, and it's something one can use for scenarios with some caution, and then it's something that can be iteratively improved as we improve the input data. So like we mentioned, like understanding where to add information about spills and that kind of stuff more explicitly can help us improve the model in ways that we can't do with just modifying parameters. So I'll show you now some of the output processing that goes into determining what the model performance is, and then one would feed back into altering the parameters to try and improve it. With the idea being that I'll hand over a set of codes that one could use to run if you then change the model yourselves. You could rerun it and then look at how things change. So the basic steps for processing the outputs of a model to check the performance is to, firstly, we need to format our observations data. So our streamflow data, reservoir data.
Sorry,
Hi.
Julia. Sorry, I just wanted to check if you are sharing anything or.
Oh, sorry. I thought I had started the screen share. Let me come back. I just started sharing thank you for that. Cool.
Thanks.
Yeah, sorry, I hadn't gone to any content yet. So here's the content one. Apologies. I thought I hadn't clicked OK. Thank you for flagging that. So the first thing we need to do the output processing for checking our model performance and our how good the calibration is to format our observed data. And so I was getting data from multiple sources, like DWS, and then UUW as well. So just getting everything into the same date formats and units, and then file naming conventions, so that I can write a code that will then find the model outputs and compare them to the observed data. So there's formatting work done, and then one can access things via code if the format's all uniform for all your various observed data. And then generating a table that links your SWAT. So when we set up the SWAT model, it breaks up channels into your stream reaches, and they have numbers in the model, and then the outputs are saved by the stream number. So you have to work out which SWAT stream number, like shows in the picture, lines up with which gauge, streamflow gauge. So that this image just shows a section of that there. So that can be done in GIS, and you make a table of that. So I've made tables that link that, and then you can write code that will access the SWAT output files. So we did a session a few sessions ago where I took you through the various SWAT output files. I'll show you that again briefly. And I'll show you a code setup for just as an example, and then can look at what else we might want to code in terms of analyses. But what the code would have to do then is find the SWAT output data in the SWAT text in out folder. And then it will find the relevant observation data that matches based on that linking table. And then, line them up in terms of dates, and then plot the modeled versus observed data. And I've set it to make various kinds of plots, and then save them so you can have a look, and then calculate performance statistics like error and errors in the highs and the lows, or errors in the mean, the p-bias, which is that percent bias that we talked about. You can calculate things at daily time steps, monthly time steps, can do log transform calculations of these statistics as well, so that the low flows are weighted more, and produce a set. And then one would then go back and check and have a look at what's happening and see, does it make sense, what parameters to change, to try and see, are the low flows to adjust against if what's going wrong. So if it's high flows are too high, it can be that the curve number that generates the runoff is too high for the vegetation types, and see if it helps to tone that down, for example. Or if both low flows and high flows are too high, then the model's just too much of the water is leaving and there's not enough evapotranspiration, and then you can change the soil storage, etc., and look at what's reasonable to change and where the parameters are. But the code that I wrote codes that I've been writing to do the model versus observation analysis, I originally wrote them in R coding language, but I'm moving them over to a format that more people seem to be using now, in Python. People still use R quite a lot, but there's also, it seems like more and more people are using Python. And AI helps with translating and writing code a lot more than when I first did it. So this is a faster process. But I believe some people spoke about having used coding before, or my hope is that I'll be able to hand over some of the analyses codes and somebody would be able to use them. Part of the, if in future, if you rerun the model with a longer climate time series, etc. And I'm happy to have subsequent meetings. The reason I hasn't handed over yet is that some of the calibration, etc., is still ongoing, which I'll get to, but I'm happy to have more one-on-one meetings with whoever is running codes to do this if they want to do it in future. But to give you an idea, so I've been using VS Code. Let me actually just show you some of this quickly. I'm just going to escape the presentation. Oh. And show you. So I mentioned having a table that links, so you have to, one of the things, a step in doing this is creating a table that links the SWAT channel ID to the flow gauge ID, or to the water quality monitoring point. So I have these codes that came from the UW database of water quality modeling points. And then I also, in that table, I've also noted what is the major river catchment that point is on and the section of river name in as much as I could find from GIS, and some other sort of information about it so that when I look at the flow performance, I have some idea of where this point is and what would be influencing it. So, is it upstream or downstream of the major dams, that kind of thing. And the catchment area of that point, is it further upstream? Is it further downstream based on the catchment area feeding it? So I have a table like this that then the code will open this table and look for each, I'll tell it to look for each flow gauge for the flow gauge, find the flow gauge, like just go through this list of flow gauges, find the data file that has the data for this flow gauge, find the output that has the model output for this channel. So for example, so for gauge U7HO12, which is on the Lovu or on the Nungwan part of the Lovu, find that gauge, find that channel in the SWAT output, line up the data, plot it, and calculate statistics. Then go to the next one. And then the SWAT output data is in, when you have your model folder, the SWAT, if I go into my uMngeni folder, so this, when you run a SWAT model, it creates when you set up our project, it creates these folders. In the scenarios folder, it has this text in out, and that has this long list of files that the model, some of these files are model inputs and some of them are model outputs. And in a different session, we went through what some of these files are and where to find information about what they are on the SWAT website. So you can see like the water balance, or like if you went on the SWAT website, you can see the different kinds of output files and their file naming conventions. So if I wanted to look at stream flow, I can look at channel. So if I wanted daily stream flow, I could look at channel SD day, and you can see that that output file would have all of this information. And if I want the flow, you can have flow into the channel at the top, the upstream end of the channel, and flow out of the channel at the the downstream end of the channel from the model. So that kind of information is in this channel SD text, .text file in my folder. So if I open that in Notepad, for example, you can see the format of it. So it has all the channel numbers, and you'll notice there's missing numbers and stuff because some of the channels got merged from the original numbers they were given. And then it has all these outputs for them. And then there's flow. So it has every channel and every day in this huge long file for the whole model run. So all of the channels, the outputs for all of the channels for all of the days is in one big file, one big text file. So to do any performance calculations for an individual channel, you would then want to pull out all the entries for the channel you're looking at. So if it was, if it was channel 3, then I'd want to pick out all the channel 3 entries. So you'll see there are lots of channels, and then so it would go and find the next channel 3 for the next day. So this is the second day and go down. And so you want a code to pull out the data for the particular channel that you want and make a time series just for that channel and then plot. So that's what I've coded, for example, in this is a Python script. Has anybody worked with Python scripts or Jupyter notebooks before? Some people mentioned that they had used some coding, or could run code that somebody else had written. I just wanted to check if people had familiarity with this format at all. Feel free to jump in. I'm not hearing anyone, but feel free to unmute and
Yes, Julia. Some of us have got some exposure using Python.
okay, great. I was wondering, have you used it in what software? I've been using VS Code as a code editor. So that's this software. VS Code editor. It doesn't show you the.
I'm not sure about others, Julia, but for me, I usually use Spider for usually it's assignments and yeah.
Okay, Spider. I haven't used that one, but it should be, these files do open in multiple different code editor programs because the language is the same. The file format I've been using is what they call a Jupyter notebook. Have you used like a Jupyter notebook file at all before? The reason I ask is because I can save things into other formats as you need, but we can discuss that more as needed. But you can let me know if Jupyter Notebook is a good format to use. What I like about a Jupyter Notebook format is that you write the code in blocks, and then you can run all the blocks, or you can run an individual block, but it shows you your output by block in the code editor, so you can see it just makes it easier for me to see what I'm doing as I'm doing it. So for people who won't be working with the code, you don't need to, I don't want to get too much into the nitty-gritty of this, but one thing you have to set sort of your file pathways. So where is your SWAT output? And which file name do you want to call? And so it's calling that text file I just showed you, the channel daily output. And I've tried to make things generic so that if you put your SWAT folder somewhere else, you could just change the path to where it is. And I'll add some more annotations to that. And where your observed data is sitting. And I've put all the observed data, for example, in, let's see, I've compiled like raw flow data. Opening it. It's like to open it. But I'll give you the observed data set that I've formatted. And then the code to put, so this one file has the observed data for all of these gauges with gaps, obviously when there's data missing in one file. The other way, you could have individual files for each one. I just found it useful to line things up to see what was when different gauges had data versus when other ones didn't. So that's why I put it all in one file to be able to see that. Oops. So it's calling that file, and then it will pull out the column of the gauge that matches. It'll run through the different, and then I have my table of which gauge matches which channel in SWAT. And then there's some code about how to open the SWAT like the formatting of the SWAT data. And then you can see that it opened it there. And then I have something about pulling out the list of gauges to use and the list of the channels. And then it loops through. So it says for each gauge where I have data, pull out the data for that gauge, pull out the data for the channel from the SWAT model, plot them, save the plots. You can have calculating statistics and save the statistics. So this one doesn't look good because I just did something to the model that didn't work, but you can see it would plot these and save them. Although this is showing what might be a rainfall data issue in that these two stream flow events had really high observed flow compared, and then the model had sort of medium to low flow peaks for those dates. So that might be more about the rainfall than the model itself. So I'm checking things like that in this particular area. But then it would plot as many, it can plot the model versus observed plots, different kinds of plots, and save them to a folder that you specify. So you can specify where, like I've given it a path saying I want to save my figures to this output folder, and then it would save them there. So we can talk about what it is, like what different outputs you would want to see as well, and modify those the way that I've set things up here. And then, based on ways that the model is getting things I want to adjust, what I have been adjusting often are the curve numbers for the vegetation types, some things about the root depths and the soil depths, and some of the groundwater outflow parameters. There are some calibration tools in SWAT, Plus. But this one is, what's nice about this tool, this one's about changing parameters in batches by a certain amount, as I mentioned. And so you can set, this is a list about parameters, but it suggests min-max values to look at for various parameters based on literature, but you wouldn't want to use all there's too many of these. But what we can do is to add a parameter, and then by creating a record, and then you can say like this is the available water holding capacity of the soil, so that's a key one. Curve number, CN, yeah. This is the curve number, for example. So here you can set the types of changes you want to experiment with. So you can change the value of the parameter by an absolute value, so that's adding or subtracting a certain amount. Oh, sorry, this is changing the value to a specific value, but it's going to change all the curve numbers in the model across all the vegetation types. So in this instance, for a curve number, you wouldn't want to do this one, but you could change the value by a specified amount, and that would take all the curve numbers for all the different vegetation types and either add or subtract like 5 or whatever number you put in. So I could put in 5 and it would add 5 to all the curve numbers of all the vegetation types. Or if I put in -5, it would take them all down by 5 or 10 or whatever. And you can add multiple different kinds of changes you want to check and tell it to run them. The other thing you can do is change the value by a specified percent instead. So instead of adding, you could change by 10% or 10% or minus 10%. So if I wanted to change them all by 10%, I could save changes and it would add it and say, where do I want to do it to all of them, or do I want to do it to specific subcatch? So yeah, so I can select to just do it to certain vegetation types, or I can do it to all of them to maintain the relationships between them, but the ranking relationships between them. They'll all be 10% higher than what they were, in the soil. So you can change it for a subset. So the old SWAT didn't have this automated within the software. So I was having to do things like this in a separate program. But so you can choose to add conditions, or you can just run a batch and see what it does externally. And if you want to do a lot of statistics, it does help. I find it easier to code it up to do it outside of the program. So that's what I've been doing, because it's easier to specify the various statistics in code than it is here. So I've been setting a few adjustments, running it, and rechecking how the performance statistics have improved or gotten worse across the different points that we're evaluating at. Is this process making sense to people? Feel free to ask questions if need be. So I'm taking you through this process in case anyone wants to engage in improving calibration on their own going forward, beyond what I'm able to do within the confines of the current project. It's also an option that I do more outside of it, but we can come back to that. But then also the same process would apply in terms of processing the outputs when one's running scenarios. Oh, looks like my model's frozen for some reason. Okay, I will come back to that. It's got a wheel that's frozen. Okay. So let me show you what things were looking like in the previous model, and what I calculated, the kinds of stats that we output for that version. So when I was doing SWAT 2012, excuse me, sorry, looked at 24 different streamflow gauges, and I did about 25 different trials of adjusting parameters. Mostly was adjusting soil depths and storages and the way that the recharge worked, because the initial parameters, there was way too much water coming out and not enough evapotranspiration. And so those changes, within ranges, and then controlling the recharge and the groundwater outputs improve the stream flow like a lot from where it started with the initial estimated values for the different vegetations and soils. I've improved the way the soils are input in this model to make changes to soils easier in this round. What I did see was that as I made changes, some areas will improve and some areas within the whole catchment area get worse. And I did some individual localized changes as well. But that's something that's going to happen up to a point, and it's going to be tricky to have a unified model that has the same levels of performance everywhere. Because it is the model represents, the diversity of soil types and rainfall and other things, but it is generalized soil types and generalized land covers, and other things are going on that are not represented in the model in different parts of the catchment. So at some point, you don't want to make one place great and one place terrible, and you kind of find somewhere in between. At about 40 water quality sites, but the performance across them really varied hugely. And so I did some adjustments, but part of it also was understanding what's coming off of different urban areas. In addition, so that the water quality would perform quite well right close to a point source. Like things performed very well right next to the Darville wastewater treatment plant because I input the observed how much I input the effluent of that wastewater treatment plant into the stream in the model. And so right close there, it would match quite well because that was just what was observed already. As the stream flowed further down, the attenuation things changed, and the water quality in the model wasn't actually diluting as much as the observed suggests that it did. And then the similar was happening at other wastewater treatment works, and then some areas had too high and too low. So looking at, I'll just show some of the stream flow results of the previous model to show you what I was talking about with some areas being better and some areas being worse performance in the previous model. So this is just a table of the different stream flow gauges. And then I also used the dam balances to estimate stream flow flowing into Midmar, Albert Falls, and Ananda and Hazelmere. So there's not a gauge right at the inflow that I could find, but if there's a good estimate of storage, outflow, and evapotranspiration, can estimate what needed to flow in on a daily basis to achieve that balance and get a estimated stream flow time series for those reservoirs. So that's what was compared. And these observed data sets covered a bit different time periods. But this column here shows like the error in the mean. So this is the observed and the modeled mean flow, stream flow in cubic meters per second. And then this is the difference in the mean in cubic meters per second. Apologies, the top of that table got cut off with the units. And then the mean, this is the error in the mean as a percentage. So you can see there's like, for the lower, a small percent of, sorry, a small difference when the flow is low can be a high percent. So when the flow is higher, a difference in the same amount can be a low percent. But like a relatively good performing area was the uMngeni coming into Midmar. So I've colored it whether it was over or under predicting. So you can see in some places it's blue and it's over predicting, and then in some places it's red, means it's under, the model's producing less water than we think should be there by this amount. So like the inflow to Midmar on average was the average was 4% less than the observed. So it was very close. And okay. Some of those numbers are okay. But it was a 4% difference that was, I see some errors in that table, but there was a 4% difference, and the Nash-Sutcliffe coefficient was 0.5, which is okay. You want it closer to 1. The low flows were better, and then the R squared was 0.55. So that was a relatively good performer. This looks at the low, median, and high flows and the percent errors in those. So you could see for this one, like the low flows are not great. The middle flows are pretty good. between the 75th and 25th percentiles, and the upper flows were within 9% of the peaks, for example. That was a reasonably good one. It was looking less good around like Msunduzi, for example, and there's a lot more urban area around there where things get more complicated, and the model had a simple representation of that. And I struggled with the impervious areas of the urban areas, which I've tried to fix in the current model. So I'm hoping this can get better than it did in the previous model. So I'll show you what this looks like in terms of plots. So this is an example of relatively better performance of that inflow into Midmar on the uMngeni. This plot is monthly observed and modeled. And this is like a zoomed in of a daily one. So you can see it's getting the median flows. All right. Some of the peaks on a daily basis have mismatches in magnitudes of size. And sometimes that's errors in the rainfall data that's hard to fix. Because, but if we're using it in a scenario context, as long as the balance of peaks and lows is reasonable to what was observed over the long period, it doesn't matter as much whether this individual event was perfectly modeled or not. If you're using it in a scenario type context, it's more, is the balance of highs and lows over the years representative to what we see, so that you can see in this flow duration curve. And it's not quite, it's hard to see at the upper end, but it's not quite getting the peaks high enough. The modeled is the blue, again, the observed is the black. Around the median, which is here, this 0.5 or 50% exceedance probability over here, it's matching nicely. It's a bit too low on the base flows. But what my concern was a little bit was that the performance was getting worse. I was evaluating performance over quite a long time period, and the better fits were earlier in the 2000s, and the performance was getting worse in the more recent period. Which is the period we're more interested in. So now in this round, I'm calibrating more focused on the more recent period and using the current land cover and the HydroNet data. So hopefully this part will hopefully get better. I don't know if this has to do with any loss of data quality in the recent period for any of the observed data, either the streamflow or the climate versus some of the older data, or if it's just that I was trying to calibrate the model for the whole time period, and so it fits. That was what happened when I tried to do that, that the part that was easier to fit well was this middle period. So in this current iteration, I am trying to get it to focus on the more recent from, also because of using the HydroNet data as the climate input, so from 2020 to current, and trying to get similar stats to what we got in the previous model, if not better, for this more recent period. And then a demo, oops, sorry, that I was supposed to check this is demo poor performance. I need to change that text. As you'll see as well, like this one on the Msunduzi midway down, it performed fairly well in the early 2000s, and then it fell apart going onwards. However, the data here looks quite suspicious. Well, it doesn't because then the model actually this period of flatlining. Oh, I think no. Okay. Pardon me. This section of data was missing in the observed, and I need to fix the way the coding for the plot. It should just show a gap there rather than a straight line because there's missing data there. Yeah. but it does start to lose these high flows. So it did well at the beginning of the time series, and then it lost it for some reason, and the observed peaks are much higher. So what's likely happening there is the way the urban drainage is working as the catchment gets more urbanized. But it could also be something to do with the gauge. It can also be intensities of events. It can be that this very high flow event in, what is this, 2018, that value might be a problem with the weir, or maybe it was real, but I'm not sure. Was it that much higher than everything else from 2000 onwards? So there may be some, because we do see, so like 2018, we don't see such a high peak for that same time period in the mid-Mar inflow. So it is possible that's a data issue. So what I'll do is plot some of those against each other, and I might have to pull out some events in some of the weirs. So I started doing that in the previous one, but then we moved over to this round. So I've identified a few events like that. So pulling that one out, if that's not, if that peak is an issue with the weir rather, would change the statistics and the calibration. In terms of the current model, there are some challenges with part of the reason that the calibration is not done as was intended by now is that I've been having an issue with the way that SWAT Plus does the reservoirs. There's something called a decision table that's a new way of inputting the reservoir outflows. And I've done so many trials, and it's not giving me the outflows below the reservoirs that I'm specifying, and it's not giving the water quality below the reservoirs that matches what the water in the reservoirs is being predicted to be. And so I've been meeting with the SWAT Plus developers to see what's going on. And it might actually be a bug in the way that this version of SWAT does the observed release specifications. So I'm trying to, so that might be fixing. So what I've been doing is just focusing on the gauges above the reservoirs, but that's a bit limiting because there's a lot of area below Midmar, etc. Like in this catchment, there's a lot of areas below the reservoirs that we care about and want to model. So that's one. And then I also discovered that the barren land cover entry, which is not a huge proportion of the catchment area, but it is a decent one. They changed the coding for that between the old and the new model, whereas all the other land cover codes stayed the same, but that one changed. And so it actually didn't throw an error. It let me proceed. And then when I tried to look at if I should be changing the parameters for that, I noticed that it's using a vegetation cover rather than being barren. So I need to re-input that. So I've had some setbacks there. What is promising is that the initial performance outputs for the model in SWAT Plus, like using the first set of parameters, look better than my initial first set in SWAT 2012. But I've adjusted soils and groundwater and vegetation to a certain degree, but I'm hesitant to keep doing that until I get this reservoir situation sorted out. And they've been taking a long time to, it's tricky because they don't have an obligation to me necessarily to fix this in a hurry. But they do want to fix it. So the other options, there's another option I can use in the meantime, which is to, instead of have the model draw I can input the observed flows downstream of the reservoirs and the observed water quality based on the data that you have, the water quality data that we have from the reservoirs, rather than having the model pull what it's done. So I have some alternatives that I'm going to start implementing now because they're taking longer to get back to me on a fix for that portion of the model. To continue with the calibration, what I can do is just sort of cut off the reservoirs and then put observed downstream flows and observed water quality using the monitoring data downstream of the reservoirs rather than having the modeled outputs there. So that's where I'm at with that part. But unfortunately, the performance statistics are still a bit worse than these ones. This is at the end of the various trials. So just to come back here, I did manage, what's nice is I did manage to get all the errors at some of the big flow points. So like the inflow to Midmar, the error in the mean was 4%, Albert Falls within 8%, into Henley, like 1%. So some of the bigger, into Ananda Dam, 1%. So Hazel, I got the basic quantity of water reasonable at some of the bigger inflows into the reservoir. So that was promising. And I'll be able to get back to that. Some of the temporal patterns did have issues, however, though, and the more urbanized areas had more problems. And I think that's the area that the urbanized areas and then the agricultural areas. So the agricultural areas were working better than the urbanized areas in the previous model. And there will be a limit to how well that can be fixed, given the way that the model works, but it in the process of improving it. So I wanted to take us back to, oh yeah, this slide. So my next steps there are to put in those, if I can't get the dams fixed in the next week or so, then I will just sort of have the dams be an end point and have starting points below them using observed water quality, in as much as we have it, and filling in the gaps there, to try and finish the calibration of the downstream areas. But what I wanted to talk a bit about now, for the time that people can remain on, first of all, if there are any questions on the process, and any inputs on the process, and then also thinking about what you're hoping to use the model outputs for, what kind of analyses of errors and areas within the region are you hoping to have, be the best performance, or to focus on in any more detail than any other area? Any of those kinds of questions. Do people have thoughts on that? Please, feel free to unmute and just. Hi, so I see you. Okay.
Oh, yes. Hi, Julia. Thank you. I'm sorry, this one is not mainly on the calibration question that you just asked, but it's just a question from my side generally. I just want to find out, Julia, if the model is able to account for the natural dam turnover processes. For example, where you find situations where in winter, the bottom water sort of moves to the upper surface, and the upper surface water, that upwelling and downwelling process, is it accounted for in the model? Because I mean, it is seasonal, and it does actually affect water quality in addition to all the other land uses that we were talking about that are inputted into the model. Thanks.
Yeah, so within SWAT, the reservoirs are more simple than we would like them to be. So part of the project was to tie in with work that Jason Hallows was doing, using a more detailed like model of a set of the reservoirs. I think Midmar and like the large ones, Midmar and the Albert Falls. Oops, sorry, slides advancing. So yeah, SWAT assumes that the reservoirs are evenly mixed. So that is a good point. Maybe there isn't actually, maybe using observed water quality as an input downstream of the reservoirs is a better plan in any case for this model setup. You bring up a good point, because what SWAT would do, it'll look at the quality. It does consider settling in terms of sediment size, but it doesn't have the temperature upwelling process being modeled. Let me just escape. We can look quickly at what it's doing there. In terms of water bodies, so it does sediment settling, and then the outflow will be, and then it has processing for nutrient transformations, but it doesn't have temperature upwelling and turnover described. So the nutrient transformations will have to do with settling and what's attached to the, huh, why my computer is being slow to load this. Let's try again. I just want to show you. Huh. Yeah, but in short, it is not going to capture the seasonal turnover due to the temperature issues of the surface and the bottom. But I'm glad you brought that up, actually, because that makes me maybe feel better about not having the flow over the reservoir, the water quality being drawn from the models, this model's outputs. So we'll try and set that part up and see how it works. I just wanted to see what it said about nutrient transformations, but it doesn't want to load. I think it's a... okay. Yeah, so that's helpful to talk about. So to come back to, so there is a limit on how many different runs and trials I can do within the time allocated to try and get the performance. I'll get the performance at least as good, if not better, than what was in the previous model for the more recent time period, given the more recent land cover. But beyond that, it would be nice to know what kind of are these kinds of plots and statistics helpful for you? Are there other particular ones you would like me to code up? Plotting and outputting. Oh, I didn't show you some of the water quality ones actually. Essentially the water quality ones. Let me find one. So for example, here's a site, you can see the modeled and the observed flow. This is TKN, total killed nitrogen, and these are the observation points. And oh, this is that's modeled and observed flow. This is just showing where hang on a second. Let me find one that shows it. But what I want to, a lot of the observation points may or may not be, where a flow peak was, or covering the diversity of flows, but that is attachment 9. So if I show you, okay, yeah, there's more observations. The TKN doesn't have enough. The suspended sediment. Okay. Apologies. I didn't have a good key on this graph. So the flow, it shows flow data in the black, and then the blue is actually the modeled nitrogen. So what you can see is that in this case, the modeled nitrogen is really following the stream flow. Whereas, so it's higher, it's the modeled nitrogen in this case, or TKN, I should say, is lower than the observed. The observed are dots at this site, are the observation at that point. I mean, that point in time. And so the model is predicting higher peaks in nitrogen at the peak flows, and then lower values than observed at the low flows, generally following the stream flow, more so than the observed data suggests. So what this would say to me, for example, is that also some of the observations are not catching the peak flows anyway. They weren't taken at the peak flow timing. But some of these spikes in the observed flow where we don't see any spikes in the model can be about leaks that are not represented in the model. Some of the higher low flow nitrogen can also be about wastewater releases that are more constant, that are maybe not being represented or processed in the model the same way, or it can be also about detection limits of the test. But in general, so we still want to get the low flow nitrogen higher in the model if possible. But this may not be as constant. It's a bit suspicious how exactly constant the observed data is in the low flows, but trying to get the model in the ballpark of those, for example. So this is just showing what can plot in terms of modeled versus observed for water quality and flow. Apologies, I need to put a better legend on this figure. Just showing that the black line is the stream flow and the blue line is the modeled, and put it on top so that it's easier to see. Maybe a different color as well. Sorry, it's bringing this out to me as I see it. But these kinds of figures, and then trying to get the performance improved. I mean, I've coded up how to output these figures, and then I can rerun the model and reproduce this figure over and over and see how it's looking, and then also output statistics. Oh no, did you have any questions or inputs at this point?
Not a question actually, but I was still just gathering my thoughts based on your first question in terms of how are we going to use this model going forward. And I was thinking I think you also touched on areas of uncertainty, and some of those areas we don't have full control of in terms of input data and other issues. But I was thinking that I feel like we can use this model maybe for identification of key hotspot areas that maybe contribute to water quality decline within the catchment. I was also thinking that for now, if we can maybe be able to use the model outputs to identify those and maybe plan interventions around those areas. I think for me, this would be maybe a success. Even looking at the scope of the project initially, it was very, very huge. But I think if you can maybe try to tailor the model in terms of identification of key hotspot areas, then planning interventions around those areas. Yeah, I didn't have any question, but I was just thinking about that.
No, that's a helpful one. Because we can use, the thing is that the use of it can develop going forward as we improve the input data. I feel like these kinds of projects I think they work best if it's like an iterative long-term type of thing, because it's a bit of a beast and you have to modify it as you go, as you realize what is not working and what's working well and what the limitations are. But I think identifying hotspots it can help us identify hotspots from a land cover point of view. Hotspots from spills or like sewer leakages that are not being represented in the model. I think that's one thing I've had challenges with in some of the urban areas, is putting in those, like if we want to use it in a scenario context, for example, or try and understand the relative contributions of land cover versus spills, or sewer overflows. I think just knowing where and when sewer overflows were happening, we can add that. So I know, but to actually input, I think what one could do is like flag that in the plots when we have data on when they occurred. So like that plot that I just had up, I shouldn't have closed that. Let's see. There's one. Oh, that's not a good one for looking at. All right, so, oh, here's one. So again, this is like the blue is modeled stream flow. The black is modeled, okay, this is sediment now. The black is the modeled sediment, and the red dots are the observed sediment in milligrams per liter. And this is subcatchment 150, which is on the sediment. Eight. 150. XP. Okay, so this is on Mkomazi. Okay, this is by Home Farm Dam, for example. Just for context of where this is, and we do see. Okay, so maybe sewer outflows in this particular one aren't relevant. We do see the model simulating too much nitrogen, but it is capturing that nitrogen's going up and down with high and low flows, the way that the observed data is suggesting, but it's too much. So through calibration, I think there's too much fertilizer being applied in the model, or there's too much of it washing off. So through calibration, I can bring the black line down closer to where the red dots are in the high flow periods. But the fact that the red dots are going up when there are peak flows is showing that there is fertilizer or manure. Oh, sorry, this is sediment. Sorry, sediment washing off. I thought we were still in nitrogen, but for that example, so there's too much sediment washing off in this case. Yeah, but there is quite high sediment. There is higher sediment. It's getting the low flows. Okay, in terms of sediment, it's not zero, but it's capturing that. But if we imagine that this was nitrogen or something, for example, if there's a time where the model is not fitting the observed very well, but we know we have like point in time data that there was a sewer spill upstream of where this point is, I can flag that, and then when I look at how well the model is performing, I can say, okay, I'm not going to expect it to perform well at that point because there was actually a sewer, or like I know why the model's missing it, unless I can see what in terms of the sewer leak we could put in. But looking at the calibrations in the agricultural areas, can try and see what the relative contributions of those areas might be. The more urbanized areas without sewer leaks being explicitly put in as like a time series of outflow, it gets tricky to get the model to perform well because it doesn't know what happened, and I need to put in what happened in some way if we want it to fit well. But we can also put in scenarios of what those sewer leaks look like and then compare that output to the contributions from agricultural cover types. So the sediment, yeah. If that makes sense. So in terms of identifying hotspots, areas with sewage leaks are always going to be hotspots, and we can identify that outside of the model. But in terms of land cover and wash off, Um, and I think it can still be used for scenarios. It would just be a question of what those scenarios should be that would be interesting on your side. Like things that are potentially achievable, or like scenarios could, we'll talk about scenarios in the next session more, but just to propose that, like, even if the performance, we'll get it as good as it can in the time, but it won't be perfect, but we can look at, like, given the error that it still has, you can still say, relatively speaking, if the change that the scenario predicts is quite a lot bigger than the degree of error, then you can still use the modeled scenario to say something like there will be a notable increase or not, or the increase that's predicted is smaller, increase or decrease in something that is predicted. If it's bigger or smaller than the model error, if it's bigger than the model error, then we can say that it's very likely that we'll still see this impact of this scenario. It's larger than the amount of error in the model. But then, you know, the more uncertainty there is in the model, then the larger we need to, you'd only want to use it to model things that we think are going to have quite a big impact, not very small changes, because the model's not precise enough to look at small changes in management or land cover. So when that's what I wanted to chat through, and the next time we meet is what kinds of scenarios of change, if we are going to use it for scenarios of change, do you think are reasonable and interesting to look at from your perspective in terms of helping you manage things? Or so scenarios can be land cover change scenarios, they can be fertilizer or manure, or it can be wastewater works inputs changes. It can be things like adding new wastewater works or changing the outputs of the wastewater works of different ones. Adding or removing point sources that represent leaks. So it'd be good to think about those things. And then I'm still working away on the calibration parts. As I mentioned, there's been more setbacks, and then what happened is I have competing projects at the same time, and so my time is a bit more spread out. I'm still able to give time to this project, but it's more spread out than it used to be because the other things have started. Which is why it's been trickier to schedule now in the last few months. But actually, this input was very helpful to think about this, that overturning in the dams, and that maybe it doesn't matter so much, that I should just actually not try and get the model to have the outflow of the dam. I should just put the observed data in. That does the problem with, well, not the problem, but the slight issue with doing that is that if we run scenarios that would change the outflow of the dams, we'd have to look at how that's being modeled. If I'm still using the observed of what happened, that input wouldn't respond to the scenario because I've input a time series for it, rather than letting the model calculate what the flow out of the dam would look like for the downstream areas. But we could still look at scenarios more focused on areas upstream of the dams, or just the way that we look at the outputs would have to recognize what we're doing there. So I'll still try and chase that up because it would be nice to fix it in the model, but if the overturning is quite a big effect on the water quality coming out of the reservoir. Is that something you've looked at quite a bit, like what's flowing out of the reservoir to the areas downstream? I saw that there's some, I haven't looked at it in detail in terms of the water quality data that's taken at different depths in the reservoir. And then what flows downstream. I know there are some observations being taken at different depths. Is that something anybody in the call has been looking at?
So yes, Julia, they do take samples at different depths and different lengths across the dam. So they've got, for example, sample sites at the inflow, sample sites towards the dam wall, and then within the dam main basin by the dam wall, they do take that sample. It's called an integrated sample where they take different depths within the main basin. So I think that's the data you're talking about.
Yeah, I was looking at the integrated ones. Now I'm just thinking about which one I should use to try and assign a water quality to the outflow, the spill over the dam wall. And I'm guessing it would look most like the water at the top. I'm just wondering if in these like high flow events, if you see a lot of mixing at a high flow, or if it like what's at the bottom stays at the bottom even when there's a high flow event. But I can also talk to Jason about that if they've. I just thought I'd ask if anybody's aware of that process. It's something to just add that as a note, something to flag. Okay. Okay. I'm hoping what can think about because we can come back to these questions as you think and talk, and I don't want to keep people here if we're not adding you need more time to process and think about it. And I will keep trying to improve how it's functioning in the background. But as you think about it, if you have ideas of ways, like outputs you would like to see presented, and like focus areas, I will think about how to present hotspots. I think what to think about is also how to use it to look at, what kinds of scenarios you might want to look at using the model in terms of changing any management operations or point source inputs If you think looking at land cover changes or specifically are something that you want to do with this model, we can do a certain amount, and then I can also, what I would do is describe how one would do different kinds of scenarios and input them into the model. There are different approaches depending on the kinds of scenarios one's interested in. Like changing the land cover requires like redelineating the HRUs, for example, which is remaking a land cover map and stuff. Whereas changing point sources is a different way of inputting, or changing climate or things like that. So, and then what output analyses you'd want to do to look at the scenarios, and how to code up doing that. So I'd go through approaches for how to do different kinds of scenarios, and you could think of what would be different ones that you're interested in doing at this point. My understanding was that there was a wish to do some scenario modeling at some point, but I wanted to have more discussion about what exactly those could look like, and then the limitations of how we use the results based on what the model is representing or not representing. So I think what would our next, we have another session scheduled as a group. I'd planned for one more session as a group, and then I am happy to do some more technical meetings. Okay, the next one was, I have it scheduled for Monday, next Monday. And we can chat more about any thoughts you have on these. I'll chat about how what kinds of scenarios one could do, and how one would operationalize that in the model and operationalize the analyses of outputs. It won't be as long. I think it'd be rather 2 hours than 3, more likely, given the where we are. But then I will have more like some handover meetings with the model when it's at a calibrated stage, giving you a tour of I'd hope to be able to do that already, but as I mentioned, we've had some setbacks that I wasn't expecting, in terms of how the other error in the model code potentially with the reservoir issue. But I will do a handover where I have sent you the model and the coding, but maybe with any subgroup of people who are actually going to be the ones hands-on running the model. And I'm not sure if everyone on all of these calls is going to be that. So this was more getting the conceptual overview so you can input into what is done on the technical side, but whoever might be the technical custodian of the actual, running the model on your computer, if you're intending to do that, and running some output, if you want to make your own changes, that I can do in a separate meeting with a smaller group, and doing share screen on your side once the model is in a better calibrated state. Is that reasonably clear in terms of way forward? And does anybody have any questions at this point? Ntando, I'm guessing would you be one of the people who would be running, potentially having the model on your computer and doing any?
Yes, Julia, that was the initial thinking, but I'm not sure. Futi will decide who else will
Okay.
be. Yeah.
Cool. Yeah, we can talk about who all, but I think that more technical, like making sure it's running on your side and the codes and the file formats and stuff. I've given the overview of it, but I wasn't sure it was also, but I don't want to hand it over now because it's not functioning as I'm hoping it will. But when we get there, just to think about who all needs to sit through that or not, and then I'll schedule that part. But I think what would help, the idea of this was so that a broad group has an idea of what kind of data is going in, what it's doing, what it's not doing, what kind of data we need to compare the model outputs to, and the process around that. Yeah. So I think I'd like, unless anybody has anything else they want to add or ask, we can leave it until next Monday, and then we can you guys can think more about ideas around scenarios, and performance, like ways of presenting performance and looking at it across the modeled regions, and if there's anything you'd like to add over and above what I was doing as a first cut in terms of just those basic statistics and high flows and low flows, and some plots. Yeah. If there's any sort of operational statistics you need or would want, I can make sure to output those or present them in a table or what have you. So all right. If there aren't any other questions, I think I'd like to thank you for your time. And I'll try and make a version where I've edited out the coughing.
Thank you, Julia, for your time as well. Hope we'll meet on Monday.
Great. All right, everyone. Oh, is Sharon on the call with one of the groups? Oh, girl. I see she was in and she left again. Okay. Okay. No, she had a software error and I wanted to try and stay on afterwards and do a share screen with her, but I don't think she's here anymore. But I'll schedule that with her separately. Okay. She was struggling to get her model running, her demo one. Okay. Thanks, everyone, and we'll chat more on Monday.
Thank you. Bye.
Bye.